So basically what it's saying is that there's a lot of ways to get, like, an example of this is like if you're going to, let's say you're going to Lincoln. You can, Google will point out different ways you can get there, right? Mm-hmm. And they'll say this will take this long to get there, approximately. This will take this long to get there. This will take this long to get there. And so it doesn't matter which direction you take, you get to Lincoln, hopefully. And so what this is saying is that it doesn't matter how many steps it takes to get to your overall reaction. The energy associated with it is going to be exactly the same. Okay? It's kind of like going up in an elevation. If you say you're 2,000 feet and you go along and you go multiple ways to get up the mountain and you get it to a certain height, the energy difference is the same. Because if I go up 1,000 feet in elevation, the work that you put in just to go up 1,000 feet in elevation is exactly the same no matter what direction you take. You're still potential energy 1,000 feet higher. And that's what this is saying. You can go through it multiple ways. So what we're going to do is we're going to do a couple problems. I'll give you a chance to write these down. Okay? I'm going to give you a little bit of time to write them down. And this will be the first one. Okay? I know.
That's one problem?
Yeah.
Okay.
But they'll be written out for you, so that's the only thing. I just didn't write them out for you. So I'll give you time to write that out. Hey, leave some space in between.
Each one?
Each one. So that if you need to rewrite it, you've got a place to rewrite it in between.
How much space do we need to leave?
I would leave enough so that you can rewrite it based upon your handwriting and how big or small it is. Okay? So here's the second one. Write that one out. Leave some space in between. Okay. So we'll do this second. This is a little bit more complicated, not too bad. We'll look at the first one first. The first one that you wrote out. Okay? Here we go. This is the way I approach it. And I don't know if I do these perfect all the time. What I'm going to do is I'm going to take and find this reactant somewhere down in one of these three reactions. Where do you see it?
In the first equation.
In the first one. You guys see it, right? Mm-hmm. Okay, so it's in the first one. Is it in any others?
No.
Okay. So you leave this one the way it's written. You'll see what I mean here in a second, how we can change it around. So we look at that one. That one's good. They're on the same side. You want them on the same side. You want whatever reactant you have in the overall reaction on the reactant or product side, and they have to be on the same side. So we'll look at this one. Which reaction has that one in it?
The second.
The second one. Now it's not on the right side. It has to be on the product side. So what you do is you rewrite it. And you just flip it. So I'm going to flip it. I'm going to put the products on the reactant side and the reactants on the product side. So I'm going to flip it. I'm going to put H2O gas plus CO2 gas, arrow. I'm going to put H2CO gas plus O2 gas. So since that's the only one with H2CO, I'm going to put it on that side. Now, when I flip it, this is what happens. The sign flips. It's no longer negative 120, but now it's an endothermic reaction, and it's a positive 520. So anytime you flip reactions, guess what happens? The energy flips. Okay? Now we want to look at H2. Okay, is there any reactions that just have H2?
The last one.
The last one, guess what?
Yeah.
Yeah, flip it.
Got to flip it. Got to flip it. So we flip it. It's 2H2O gas. And then arrow 2H2 gas. O2 gas. And we switch the sign. Okay. So what I would do then is I'd scribble through so it doesn't mess me up. The other reaction. Now, if we add these up, now, we got to get the numbers right. Okay, so how many CH3OHs do we have on the left side in the reaction we want to find a enthalpy of? One. And here we got 2. Okay, that's good. We'll just leave it like that. We know it's double. Okay, now we're going to look at H2CO. Okay, it is, there's just one of those. Is that right?
Yeah.
Okay, so we'll look at that. And then we got the H2. There's 2 of that. So this is what we can do. We're gonna divide everything in the first one by 2 so that we have 1 on that side. Does that make sense? So we're gonna take, hey, we got 2 of this, we got 3 halves of this, we got 1 of these, and we got 2 of those. So I mean, basically we got 1, 3 halves, 1, 2. Does that make sense?
Yeah.
Okay. Now if you want to write down 1, 3 halves, 1, 2, you can do that. I'm gonna leave it like that. And then guess what I have to do this overall reaction? I've got to take and divide it by 2. Or take it times 1/2. Okay? Second one I don't have to do anything with. I just have 1 of them. 1 mole of it. That's good. And then the next one, what will I have to do that one?
Divided by 2.
Divided by 2. So I go 2, 2, so I got 1, 1, 1/2, right?
Yeah.
Alright, so hopefully, by doing that, everything else cancels out, except for 1, 1, 1. So if I've got to take this times the 1/2. Okay? We'll do the math later. So what's most important is to see what can cancel out. I cannot show any waters. Does the waters cancel out? So over here I have how many?
2.
2.
Oh, yep. And so I have 1 here. I need some, and I got 1 here. So they cancel out. Good. Get rid of water. What else has to cancel out? Or should cancel out? CO2 is not in our overall reaction. Does it cancel out?
Yes.
Yeah, it cancels out. 1 and 1. We're going good. Now we got to get oxygen to cancel out. So over here I've got 1.5 on the left side. And how many do I have over here on the right side? The 1.5. 1.5. Boom. Now does everything work out right? I should be just left over with 1 of each. Am I?
Yeah.
Okay, so then we're good. We're good. We've got our overall reaction. I'm not going to rewrite it. It's up above. This is the reaction. It says when we come down and rewrite it, we'd have 1 CH3OH gas. And then I keep coming down and look, okay, nothing else is on the reactive side. I have an H2CO there, that one's fine. I come down and I have, do we have an H2?
Yeah,
Yep,
it's right
we
there.
got an H2 left over, so we're good there. I think we're good. So then everything cancels out except for one of each one of those. So then you multiply this by half. You keep this the same. So it'd be positive 520. What's half of 1353? 750. 650. 675, 676 and a half.
676 and a half.
And the sign is negative.
Mm-hmm.
And then here we have half of that is 242. And what you do is you add them all up. And then that's the energy for that reaction right here. That's what we come up with. That's the energy. So change in enthalpy for that reaction. Looks like it's positive, isn't it?
Yeah.
So what is the answer positive?
I got 85.5.
Okay? 85.5 kilojoules. So that reaction, you have to put 85.5 kilojoules into it for it to go. Per mole. Or not per mole, but just for that reaction. Does that make sense?
Yeah.
Okay, let's try the second one. Any suggestions on this one? I'll let you guys make suggestions on what we need to do. You want to do one element at a time. So let's all start with S. Is there any one reaction that just has S in it?
The bottom one.
Okay, so does it make sense to double it or not?
Yeah.
Yeah.
Okay,
Yeah.
we might have to go back and change, so we double it. It's 2, 2, 2, and then we double this. Is OF2, is it in any?
Yeah, it's in the first one on the website.
Oh, that one looks like, maybe we have to double that too. We can try it. 2, 2, 2, 4. Okay, so if we do that, we've got to double this. All right. How about the SO2? Here's the trouble with SO2.
There's two of them.
It's in multiple reactions, so I would not mess around with those compounds that are in 2 or more reactions. That's 2 variables we have to figure. So you always want to stick with the ones that are only in one reaction, and then that way the other ones tend to balance out. Kind of like balancing. Same idea, concept. All right. So the next reaction.
SF4 is on the wrong side.
So we got.
So we can flip it.
Mm-hmm.
Yeah.
Okay, we'll flip it. We'll go SO2. It's important you put gas or liquid because some of these, they get caught up on the liquid and gas. You can have 2 of the same compound, but one's a gas, one's a liquid, and so just got to be careful of that. I think for the most part, we don't have to deal with that a whole lot on these, but you just always want to be as precise as you can. Did I have that right?
We need to change the sign for the enthalpy of that.
Okay, we have to change the sign. Okay, so So sometimes you just gotta double check to see if you got it written right, because I write these out and I'll mess up. I think it's right, so I'm gonna go ahead and scribble through this original one. Get rid of them. Get rid of that guy. Okay. So, do you think, so we got 2 sulfurs, that's okay. The OS, we got 2 of those, that's fine. The SO2, that one's fine, isn't it? We got 1 SO2 on the left, and then this one we have 2. So that's subtract the 1, so you get rid of this one, and then get rid of that, make it 1. And cross your fingers. The SL4 is right. Is that correct?
Yeah.
Okay. We have to cancel out some things. Does the oxygens cancel out? They do, don't they?
Yes.
Anything else cancel out? Waters? Do they?
H4s.
The H4s?
Or HFs.
Oh, the HFs?
Yeah.
They cancel out. Good. How about the H2Os? They cancel out?
Yeah, they do.
Oh, good. You get kind of worried.
Why?
like- Well, because it's a lot of work to get to that point, and then if it doesn't cancel out, you're like,
Restart.
all right. So we got good and lucky there, and we wrote everything. So now all we have to do is add these all up once we multiply them, and we got our answer. And that's how you do Hess's law.
This is basically balancing. Just
You know what it is? It's a complicated balancing.
yes.
What's different? You got to flip things.
Mm-hmm.
That's the only thing that's different. Is that you got to flip things out, and usually in balancing you don't cancel out
Yeah.
things. We did a little bit with spectator ions.
Uh-huh.
You cancel those out,
Yeah.
so it's kind of like that.
Mm-hmm.
So what's our final answer on this one?
Negative 320 kilojoules.
Negative 320 kilojoules. So that's an exothermic reaction. The one prior to that was endothermic. Okay. So boy, I don't think I've ever went through Hess's law that quick, that easy. Okay, and so I've got 3 for you guys to do on your own. The only trouble is I got to write them out and that. I wish they were written out for you. How about this? Let me look and see if I've got some typed out so that you don't have to. I've got 3 problems picked out, but let's wait and let me see if I've got 3 that I've already have printed out copies on worksheets so that you don't have to write these all down.